Hello, my name is Simon Schrodi and I'm now going to present to you our paper Towards Understanding Adversarial Robustness of Optical Flow Networks, which is joint work with Thomas Saikia and Thomas Brox from the University of Freiburg, Germany. This project was funded by the Deutsche Forschungsgemeinschaft DFG and the German Federal Ministry for Economic Affairs and Climate Action within the KI Delta Learning project. In an initial work, Rajan et al. Showed that they could attack the optical flow network FlowNet-C and to a lesser extent also FlowNet-2 with physical patch-based adversarial attacks. In contrast, other modern optical flow networks such as PWCnet were robust against those attacks, and they suggested that the encoder-decoder architecture is the main cause. However, we found that FlowNet-S, the sibling of FlowNet-C without a correlation layer, and also an encoder-decoder architecture is not vulnerable, which does not align with their hypothesis. We find that self-similar patterns in conjunction with the correlation layer are the main cause, which most modern optical flow networks already likely unknowingly rectified. And we show how to also rectify the vulnerability for FlowNet-C by a simple architectural change. More specifically, we found that unattacked and attacked features are separated after the correlation layer of FlowNet-C, while they stay well aligned before it. This suggests that the correlation layer causes the vulnerability due to matching ambiguities triggered by the patch. And in fact, we can also handcraft a patch with self-similar patterns that causes the same effect as the optimized adversarial patches. This underpins our finding that matching ambiguities are triggered, which consequently leads to a separation of unattacked and attacked features. Subsequent layers that are supposed to interpret the feature matching of the correlation layer then successively spread the ambiguous signal into a larger neighborhood. Furthermore, the self-similar patterns of the handcrafted patch relate the vulnerability to the classical aperture problem, in which repetitive patterns also cause matching ambiguities due to a too small aperture, which is also called the receptive field. From this, we directly follow that we can rectify this vulnerability by increasing the receptive field before the correlation layer. To this end, we add more layers and thereby increase the depth and thus the receptive field. Alternatively, we can also use larger dilation rates. And indeed, the simple architectural change keeps the features after the correlation layer well aligned, and consequently, the vulnerability can be resolved. In fact, conversely, we can also show that we can make a previously robust flow network like Raft vulnerable by reducing its receptive field before its correlation layer. After looking into patch-based attacks, we found that optical flow networks are also surprisingly robust against universal perturbation attacks. However, in the white box setting, we found that adversarial attacks still work, and even worse, an attacker could potentially craft a small perturbation leading to any desired flow from a similar domain or even from a completely different domain. However, we can alleviate this vulnerability through adversarial data augmentation, which also significantly improves robustness against stronger adversarial attacks while having a negligible effect on the performance on clean data. To conclude this presentation, we found that self-similar patterns are the actual cause of the vulnerability against physical patch-based adversarial attacks, which is related to the classical aperture problem. Therefore, we can fix the vulnerability by increasing the aperture, or conversely, make a robust optical flow network vulnerable by decreasing the aperture before the correlation layer. Further, we found that optical flow networks are surprisingly robust against universal perturbation attacks. However, on the flip side, we found that they are still vulnerable to white box perturbation attacks, and an attacker could even craft small perturbations leading to any desired flow. But we can alleviate this vulnerability through adversarial data augmentation. Therefore, an attacker requires access to both the image stream and the network to be able to attack optical flow networks. Our paper and code can be found with the following QR code and URLs at the bottom of the slide. Thanks for your attention, and I hope to see you soon at our poster.